Our next section is going to discuss gas mixtures and partial pressures. And one of the pioneers of this field is John Dalton. And Dalton studied the properties of combining various gases and determined the total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. So what he showed was our total pressure, which we'll represent by P total, is going to equal P1 plus P2 plus P3 plus whatever gas that we have. So in this case, we would have three gases combined together. So if we have a mixture of these gases, the total pressure is going to be the sum of all the individual pressures. So this observation is known as Dalton's law of partial pressures. And it's significant because this law states that each gas acts independently of the other gases in the mixture. So if we think about this, we can kind of rewrite this, P total expression, because if we assume each gas is ideal, we know that PV equals nRT. So P is going to equal nRT divided by V. Okay? So if we're going to take, constant temperature and volume, we can say that P total, instead of writing this as P1 plus P2 plus P3, we can say this is going to be N1 times RT over V plus N2 times RT over V plus N3 times RT over V plus however many gases that we have. So our P total then can be represented by NT times RT over V. And this is at constant temperature and volume. The total pressure is determined by the number of moles present. And because each gas behaves independently, we can relate the amount of a gas in a mixture to its partial pressure. Okay, so if we took the partial pressure of each gas, which would be the pressure of one of the individual gases, divided by the pressure total, we can say it's going to be N1 times RT over V divided by N total times RT over V. And this can be simplified to N1 over NT because the RT and the V are all going to cancel out here. Okay? This particular expression, we came up with a specific name for this. This is called the mole fraction. And we can define a mole fraction, which we'll abbreviate with a capital X, as the fraction of the number of moles of one component of a mixture divided by the total moles. So we can then rewrite this, that N1 over NT is going to be equal to P1 over PT. So we can say that the mole fraction, or X1 in this case, is going to be equal to P1 divided by PT. So this is how we typically express these mole fractions, and these are certain calculations that we're going to be interested in, and the next few videos will cover examples of gas mixtures, partial pressures, and this mole fraction.